In the previous video, I showed the geometric construction of several harmonic circles for the fifth, fourth, and third harmonics, where the conical radius was found experimentally. In this video, I'll be showing how we can derive an equation for the general solution for all the harmonic relationships between a sphere and a circle drawn on its surface. And to do so, let me start by describing some of the pieces of our geometric model here. We have four radius involved. We have RTA, which is the top conical radius that you saw used in the previous video, where a compass was placed on the top of the sphere to draw the circle. There's a bottom conical radius, RBA, where the compass could be placed on the south pole. There's RP, which is a planar radius, seen here as the actual radius on the same plane as the circle, and a spherical radius R, which is the radius of the sphere itself. There's two angles of interest. There's omega, which is the top conical angle, and W, which is the central angle for the inscribed polygon. So what we need to do now is, with all of these various triangles we have here, we can create three different equations to use to get the general solution. The first equation is based on triangle P1, P2, CP, as seen here. It's blown up off to the side here. And we can use a chord formula, essentially, to come up with the equation 1 that shows the conical radius RTA as a function of the planar radius and angle W. Now for the next equation, equation 2 is based on this triangle P4, CP, CTA, and this allows us to come up with equation 2 that shows the planar radius as a function of RTA and angle omega. And the third equation is based on this larger triangle, CTA, P4, CBA. And this allows us to come up with equation 3 that shows the conical radius RTA as a function of the conical angle. Now that we have these three equations defined, we can solve these simultaneously in the following fashion to come up with the general solution. I'll go through this somewhat quickly, but you can pause the video at any time to take a look at what I did here. First, I'm just going to substitute equation 2 into equation 1 to basically get this result here, and then reduce it down to get to equation 4, which shows the conical angle omega equal to a function of W. Then we'll take equation 4 and subset into equation 3, and we can derive the conical radius RTA as a function of W, as seen down here in equation 5. Now, to make things a little bit more specific to a harmonic instead of a central angle, we can just basically reduce or rewrite equation 5 by essentially knowing that the central angle can also be defined as 2 pi radians, or 360 degrees, divided by the number of sides of the polygon. And we know that the number of sides of the inscribed polygon is also what defines the harmonic, h in this case. And as a result, W can be represented by 2 pi over h for radians, or 360 divided by h in degrees. And equation 5 can be rewritten as the following. And this will be used in subsequent videos to more precisely calculate the value of the conical radius for other harmonics. So now that we have the general solution complete, what we have here is a plot of the general solution, and we'll be focusing on the x-axis between pi over 6 and pi over 2. and this is where the conical radius ranges from 0 to √3. And if we look back, just to review what we've seen so far, was for the fifth harmonic, resulted in an inscribed pentagon, which led, using a circle arrangement, to the icosahedron. This is the precise value that would be used. The fourth harmonic related to the inscribed square, and a circle arrangement allows the discovery of the octahedron, where the third harmonic inscribes a triangle and results in discovery of the tetrahedron. Now beyond this, if you look at plot 1, there are points calculated for RTA that's contiguous along this curve for values in between the main harmonics. And one such example we can find between the fifth and fourth harmonic that I initially would call the 4.5 harmonic, but soon realized that this is best described as a mixed fraction. So the fourth harmonic should be represented by 9/2. As a result, we need to add one more term to the general solution to account for fractional harmonics. So we're going to add the term d to account for the depth of the harmonic, which is going to change the operand from pi/h to d pi/h. And as a result, the values used for d and h in the general solution ends up determining what sort of star polygon gets defined or just inscribed in the resulting circle. So for example, we can take the above 9.5 harmonics, where d is equal to 2 and h is equal to 9, use a general solution to come up with a approximation right here for this harmonic. Now, you know I had the number for the conical radius. I didn't know what it would look like and how it would come out on the sphere. So let's go take a look at what this would look like during geometric construction. Alright, in this video we're going to explore a fractional harmonic that we calculated from the previous video, which gave us a value of 1.257 times the radius of the sphere itself. And let's see what that leads to. Again, harmonic 4.5. So let's draw the initial circle. And now we're going to keep track of where we started from very precisely. There'll be a starting point. I'm going to label this 1. This we'll label 2. We want to keep track of where we are on the circumference of the circle. That'll be the third. This will be a 4. This is 5. Now you see we're passing the first mark, so now we're into the second part of the rotation. That's number 8. This is number 9. And that brings us back to 1. So now we've converged on itself. And what we've done is we've divided this circle into 9 equal parts. But you'll notice that it's every second, if we draw this out, it's going to be a 9-star polygon. Because we're going to go 1, 2, skip 3, 4, 5. Now, you can also draw this out to see the pattern it results in. Let's go back and start at 1. Now you can see a 9-petal flower on this side, and on the other side you can see a 9-sided polygon on this side. And this is what's known as the 4.5 harmonic. Alright, in this video I'm going to show the 7/3 harmonic. So this has been tuned to that conical radius. Put a first mark here. So this should take 3 rotations around the circle to create 7 equal arc segments. That's 2. Three. Now we're into the second rotation as we passed point 1. Number 5. Now we're into the third rotation. This should bring us back. This is number 7. And this goes back to the beginning. So we've divided this circle into 7 equal arc segments. And you notice we skipped every second one. There's 1, skip 2, there's 2. Skip another 2, there's 3, etc. Now let me draw out the complete circles. There's the pattern. We've got the 7-petal flower on the front, and I guess somewhat of a larger 7-sided polygon on the bottom. This will be for the 11/4 harmonic. And this is for the 11/5 harmonic.